Our objective in this video is to learn about learn about the curve fitting. But in the previous video, we learned about the how can we fit a straight line. It was a simple regression models that we learned. And so in this video, we want to know how can we linearize some of the nonlinear relationship and then use the linear rules that we would have, like linear least square rules. Then we want to learn about the polynomial regression, and we want to understand multiple regression. And at the end, we are going to look at the general form of the linear least squares. For the linearization of the nonlinear relationship, so when we are looking at it, it's like that. Think about it. There are many things in the nature that they have nonlinear relation together. For example, we have whenever we are talking about the normal distribution curve, we have some part of it is like exponential when we look at it, right? So for those ones, like for example, for the exponential or the power function or the saturation growth rate, for all of them, one technique consists in transforming the nonlinear relation into the linear one. We call it linearization. For example, for the exponential, look at here. So we would say we can get the natural logarithm from both sides. And when we do that, the thing happens is that here is going to be natural logarithm of y. And here it's going to be natural logarithm of the alpha 1 plus uh, natural logarithm of the e power b beta 1x. And then, so it's gonna, the thing that is going to remain is going to be beta 1x. Another example is the power function. Look at here, when we have the power functions like the y equal to, like for example, a2, which is the coefficient, and then x power something, like power like that beta 2, that parameter that we are looking to find out, right, for our regression models. When we want to linearize that, again, we are going to put the natural logarithm, get the natural logarithm from both sides, and you can see that the result is going to be natural logarithm of y equal to ln of this part plus beta 2 ln of this x. The next example is the equation of the saturation growth rate. So if we have something like this, you can see that we have something in the, we have x in the numerator and the beta 3 plus x in the denominator. So in this one, it was simpler. The way that we did for the linearization, we just said that, okay, let's say 1 over y. So we try to put this one, like move this one in the denominator and move these ones, all of them in the denominator of this side. Like we changed the sides. And we are gonna find out this equation for it as like the linear one. So when we find this one, and this one, then we can go and use the linear least square equations, like the methods that we had. Let's look at the polynomial regression. Polynomial regression, for them, it's not always possible to use the linearization method that we have. Another alternative is to fit the polynomials to the data using polynomial regression. Polynomial regression is very similar to this linear regression that we learned. I'm going to show you a few examples in a few minutes. So, in fact, as you can see here, it's written the polynomial regression is an extension of the linear least square regression. The only thing is that our matrix that we want to write down, for example, the matrix of this A is going to be different. So let's assume that we want to put our data and fit it to the second order polynomial. When we say second order, it's going to be a0 plus a1 x plus a2 x power 2, and this is the residual, right, or error. And we want to, so the way that we did the same things in the least square regression. If you look at the first video on the curve fitting, which was the least square regression one, what are we going to do? We say that we want to minimize the sum of a square of the residual, right? Sum of a square of these ones, and we would say it's going to be yi, which is this, minus all of these ones, minus a0 minus a1x, because we are going to, in fact, we are moving these part to the other side to have like residual equal to something. And then we say sum of a square, and with the sum of a square, we are going to say, okay, so it's like that. We are going to square it and then have the sum here. And we had similar approach for the linear least square. So what are we going to do? We want to find out a0, a1, and a2. These are the polynomial coefficients that we would have for our x1, right? Like the variable that we have. So what are we going to do? We are going to get the partial derivative respecting to a0, then partial derivative respect to a1, and partial derivative respect to a2. So when you look at it, you can see that from the residual equation that we had on page 5. So sum of a square of the residual or error. We got the partial derivative of that equation respecting to like different functions. And the thing happening here is that we want to minimize our residual. So it makes sense to do that. And then we are gonna, when after getting we got the partial derivative, we're just gonna play with the equations that we have. So we put the like those partial derivatives. We say that the derivative should be equal to 0 on the critical point, which is like minimum or maximum. So for here, we are looking for the minimum. So when we get the partial derivative, we make it equal to 0, and then we are going to get these equations, all of these things that you see. So look at here, we have a0, a1, a2, and then again a0, a1, a2, a0, a1, a2. These x values are the coming from the data, right? So on behalf of the data, we have n, the number of the data points that we would have. This is xi, yi. So with these three equations, with the three variables, so it means that our variables here is a0, a1, a2. Be careful. So we want to find out these parameters to make our regression model. We have three equations, three variables, so it's so obvious. We are gonna, the degree of freedom is 0, so we can find it. Let's put it in the matrix form. So in the matrix form, it's gonna be like n, xi, xi2, and we have a0, a1, a2, and this is the other side of the equations. So we can, if you multiply this part, this matrix, to this matrix, and then you would say equal to these ones, you're going to get exactly the same equation that we have in the previous page, like this page. So you're going to get these equations, all of these equations, okay. So the technique that we talked about, the polynomial regression, this technique can be easily generalized to any nth order of the polynomial. What does it mean? It means that, for example, you have the polynomial of the order like, let's say, 10, right? We can use this technique. The only thing is that, look at here, when we are talking about the order 10, here is m, right? So the number of a that we have, because the parameters, like the coefficients of these x1s, because these ones, they starts with the a0, so the number of the variables that we have in our polynomial regression model that we want to find is going to be m plus 1, right? For example, if this m was 10, we would have a0 plus a1x plus a2x2 plus a3x3, and we would go until a10 x power 10. So we would have like 11 a's, right? We just need to be careful about this. The standard error, we talked about that before. So when we want to find it, for the standard error of the, like, let's say y, at some x, we would say is the sum of a square of our regression divided by the degree of freedom. So this degree of freedom, we can look at it. So it's like that I have n data points. What's the number of the parameters that I have here? And I'm interested to find them. Because these parameters, they're working like a soldier, right? So it's gonna reduce the degree of freedom that you would have. So it's like that, I just remember the Game of Thrones here. So it's like that you would say have n data points, and you have m plus 1, like these parameters, that they're gonna, each of these parameters, they're gonna remove It's like that. It's a soldier, and it's going to remove one of the degree of freedoms. So it's going to, in the denominator, I'm going to have n minus the total number of the parameters, which is the n plus 1 here. In fact, it's like that we are going to lose n plus 1 degree of freedom. Each of these data points, they're bringing 1 degree of freedom to our system. But when we are adding these, like a's, this is another way to say that. So when we are adding these parameters, it's like that we are removing some of the degree of freedoms from our system. Another extension of the linear regression is the multiple linear regression. So far, whatever we have learned in the linear regression, we just had one variable of x. But for example, it was polynomial. We had like x power 2, x power 3, or it was exponential. So we needed to get the natural logarithm from both sides to make it linear and then use the least square. This one is the multiple linear regression. It means that we have x1 and x2. We have more than one variable. So this x1 can be, for example, temperature. This x2 can represent pressure. And this one can represent like the, let's say we are talking about the distillation column. So this y can be the purity of our products. So for these ones, what are we going to do? The approach is very similar to the approach that we have learned so far. We are going to get the sum of a square of the regression of the residual. This SR here is the same as the SSE that we had before. So it's the sum of a square of the residual or sum of a square of the error. So sum of a square of the error or residual is going to be equal to the like yi minus all of these, right? This is the residual. E is residual. So we are going to sum it, like square it and then sum it. And again, we are going to get the partial derivatives. We are looking to find out the minimum amount for these residuals. And the partial derivative is going to be, because we have A0, A1, and A2, these are three parameters that we are interested to find out. So we are going to need to get the partial derivative respecting to these three ones. And then we are looking for the minimum. What are we going to do? So you can pause the video here and answer it and then come back, like listen to the rest of it. So when we want to find out the minimum, we are gonna get the derivative, and derivative is like a slope, right? The slope should be 0 when you're looking at the minimum, because even when it's like a critical point for us, right? Then the same things as before. So we are going to write down the x's as one matrix, and then our a's. However, we have this n in all of them as well. And then a matrix, and we have our whatever we had on the right hand side of our matrix. The only difference between this matrix and the matrix that we have for the polynomial was that here, for example, we have x1. In the polynomial regression, here was x power 2. Or for example, the next one, x power 3. So, but here we have x1 and then we have x2, like the first variable, the second variable. I is the number of the data points that we have, which is like equal to 1 to n. So we are going to write down this is the same equation that we had in the previous page. We have the equation of it. So we need to solve this system. So this can, we are seeing the multiple regression. The standard error is very similar to the previous one. Instead of, you see that in the polynomial, for example, this x2, like variable number 2, it was x square. Or this xm, it would be x power m, right? You can see this similarity. So the standard error of that is going to be the same as well. We are going to use this standard error later in the second year course, stats of the second year course, when we are interested to find out the confidence interval of our regression models. So it's very important that we know this standard error. You have seen that, for example, sometimes when you're working in the lab, you would say that, okay, I want to find out this number. It's like 12 plus minus 0.3. So that 0.3 or margin of error, when we want to find it, we need to know what's the standard error. So here, this is a multiple linear regression, and it can be could be particularly useful for power equations. So think about it. What are you going to do if you have something like this? Think about it for a moment. So first we are going to linearize that, and when we get the log from both sides, and when we linearize that, then simply we can say that, oh, it's very similar to this one, right? So I have the a1 log of x1, which is my first variable, my second variable, right, and my nth variable. So now let's talk about the general form of all of these least squares. We have seen that all of these that we worked on, whether it was polynomial regression or the multiple regression, linear regression, or the simple linear regression, with all of them we had this method that we would get the derivative equal derivative of the sum of a square of the residual, and because we want the residual to be equal to the 0 or be the minimum at least, so what are we going to do? We are going to get the derivative equal to 0, and then we are going to find out a0, a1, a2, and the rest of these parameters that we are interested. So from this part, we want to have this general form, write down this general form. So let's say for this general, we have a0, z0 plus a1, z1. So this z1 can be like z0 power 2, or it can be another variable. It doesn't matter. The only thing is that when we are talking about the linear in these regression models, because we want to find out these parameters, right? So in fact, our parameters, they should be like linear, should be in the linear form. Look at this one, for example. A0 plus A1 cosine of WX, A2 sine of the WX or omega X. So when we look at it, what do you think? Do you think it's linear or nonlinear? Look at A0, A1, A2. So this A0, A1, A2, they are in the linear form, right? So this equation is going to be linear. We consider it as linear when we want to work with the general least square method. Another example. So look at here, y A0, 1 minus e. So when you look at this A1, this parameter of A1, because this is in the like exponential form, so it's going to make it nonlinear. So this one is not, we can't consider it as a linear. We need to linearize that and then try to solve it with the general least square method. So now let's go back to the model that we had. We said that, okay, we have our like y1, y2 up to yn. We have all of our like z01, z11. So this is for different variable, like first variable, which is temperature, second variable, which is pressure, something like that. And then these are the parameters that we are looking for. Plus these are the residual. So we wrote down like this. Or simply we can write down matrix of y is equal to the matrix of z times matrix of A plus E, right? Residual. This Z matrix, it has n, it's like n by m. When you look at the size, it has n row and m column. So we would say that it's not a square matrix, and it's like the most of the time when we say n by m, it's like, yeah, because one represent, like, it comes from these variables, right? The number of the parameters that we want to find out, it's m, right? And then it's like n plus 1, you can say something like that. But the number of the equations that we have is like n. In fact, we can say that n, right, is equal to the m plus 1. Okay, so let's go further. So we want to get the sum of a square of that equation that we have, like this equation that we have here. So we want to get the sum of a square of the residual. We're going to write it down. It's the same things that we had before, yi minus sigma of this one. And then we want to minimize that. It means that we need to get the partial derivative. So for getting the partial derivative, what are we going to do? We want to get the partial derivative and then equal that to the 0, right? So when we want to work with that, it's like that we have we just play with the equation a little, like with this equation that we had here, right? So with this one, we just play with it. We said that a is equal to something like that, because we are looking to find out this value of A. So it's like we multiply both sides by the ZT, and then like Z transpose, and then we try to, for the next step, we try to find it. This is an example. In this example, we want to find out, so we have this equation. So 3 disease-carrying organisms decay exponentially in seawater according to the following model. And estimate the initial concentration of each organism is like this. So when you look at it, it's like I'm interested to find out A, B, C as parameters. And we don't have these A, B, C in the power of the exponential, right? So because of that, we can consider it as a linear one. We can consider linear, be careful with this one. The parameters, like these coefficients, the parameters that we're interested to find out, these have the linear relation. And because of that, we can use the general form of the linear least square. So we have T and P. These are the data points that we would have. So you can see we have 10 data points here for different at different times. We have different P for it. So we want to work on it. What's going to happen? This is the equation that we had, right? Or just instead of y, I put it p, because here y is p, right? And then we want to make the first thing is that we want to make all of the matrices. Matrix P is simpler because it's like here, I would just write down 7, 5.2, 3.8, 3.2, and you can see that here, right? And then the next thing is this one, this A, which is the matrix. If you remember, it was like, if I'm not wrong, it was n by m. Yeah, it was m by n, and so it's a larger matrix rather than this P. So when we want to write down this one, look at here, see what we are going to do. With A, we are going to write down like A1, A2, A3, right? So we have like our A1 is A, our A2 is B, our A3 is C. So when we were talking about this Z as the like larger one, which is like n by m, what's going to happen here is that the first column, it's very simple if we know the concept, if we learn the concept together. Look at here. The first column is that, because we are talking about, let me just go back. It showed too soon. It represents, the first column is going to represent the first parameter, A, that we have. So when you look at it, that's E, like what's the coefficient of this A? E power minus 1.5 t. So you have t values, right? So you're going to put the e power minus 1.5 times the different value of this t. Look at here is 0.5, 1, 2, 3, 4, up to like 9. That we have up to 9. The second column here, when you look at it, the second column, it's for finding out, like you're going to multiply it by b in your main matrix equation. So whatever coefficient that you have for b, you are going to put it here. And when you look at it, e minus 0.3t, so you're going to write down here e power minus 0.3 times 0.5 times 0, but just time is changing. And the third one, you can write it down by yourself first and then look at and compare it with here, with this one that we have. So it's the coefficient of C. I just wrote it down here, and instead of t value, I substitute that with the t value that we have. Okay, now we have Z, we have P, and we are interested to find out A, which is like capital A, capital B, and capital C here. Or in the previous one, it was A1, A0, A1, and A2. So we are going to find out, we're going to solve the matrix, and the answer is going to be something like this, like for different, like A, this A is going to be 3.77, this B is going to be 4.38, and this C is going to be 1.37, as you can see here. So in this lecture, we learned about the linearization, polynomial regression, multiple regression, and all of these, like these two, we saw that they had the similar methods, so we generalized our linear least square. The next is that then we want to find out learn about the like curve fitting, but then we have the polynomial interpolation. So that one is very interesting as well, like an interesting subject that we are going to learn together.